Hello. In our experiment, we will be experimentally finding the value for mu0, which is the permeability of free space. We will do this by sending differing voltages through different wire geometries and measuring the current with a magnometer, and using graphical analysis we will extract mu0 value out of there and compare that to the expected value of mu0. So before we can talk about the permeability of free space, we first have to talk about magnetic fields. A magnetic field is created or induced when you have a moving charge through space. And when that charge moves through space, it creates or induces a magnetic field perpendicular to the direction of motion, forming concentric rings around it. Now, when you have these charges moving through a wire, it creates a current. And that current is like the foundation for most of electromagnetism dealing with wires and different geometries. And it can all be explained through one equation. And we have the Biot-Savart law, which states that for a small section of the wire, with a current going through that small section, induces a magnetic field, right? And so when we integrate this, or just add up all those tiny pieces of the wire, we get different geometries based on the different shapes of the wire and different equations. So for instance, a long straight wire, you would end up with this. For a loop, you would end up with mu0I of 2r, and for a solenoid, the same thing. It all depends on the geometry. Now, as you can see here, mu0 is a part of this equation. Mu0 pops up anywhere where you have a current going through a wire and a magnetic field. And it explains how the magnetic fields act within free space. It dictates how it acts. And throughout all of it, we can deduce or experimentally find that the accepted value of mu0 is 4 pi times 10 to the power of -7 Tesla meters over A. Now, we can experimentally find this by using our different geometries and solving through each one of them, and with different currents, different voltages, and so on. So in this experiment, we used the different geometries of a long straight wire, a loop, and a solenoid to experimentally find the value of mu0. And we can do this by using graphical analysis, by plotting the current against the magnetic field and just solving mathematically or algebraically for mu0. And through all of this, it gets a little bit complicated because you can do this, but you would have to directly align your geometry with the Earth's magnetic field, because it also creates a disturbance in the magnetic field. And so you have to align it with that vector so that you can just subtract the magnitudes. But that's very complicated and could lead to more sources of error. What you could instead do is find a magnometer which gives you the force in all directions, the magnetic field in the x, y, and z direction. And so what you can do is you can use vector subtraction, taking the magnetic field due to the Earth, and the full, once the current is induced, or once the magnetic field is induced, and subtract them, and that would be the direction of the force of the geometry's magnetic field. And once you can do that, you can take the magnitude of that, and then you have your B, or your magnetic field, the magnitude of it, and you can algebraically and experimentally solve for mu0.
Okay, so the first thing we're going to do is measure the resistance of each wire. For the circle.
And make sure the ends are shaved off.
And then we measure the resistance of the solenoid. This is the resistance for the straight copper wire. Roughly 100.
Okay, so the next thing we need to do is attach the wire to the voltage source, and for the loop, we're going to put it right here on a conducting surface. I mean a non-conducting surface, so it doesn't mess with anything, even though it already has a cover, a non-conducting cover. So it's just for extra protection. And then we want to make sure the magnetometer, the sensor's right here. So we want to make sure that the sensor is right in the center of the loop. And then we want to measure the magnetic field of the Earth. We measured it 3 times. We just stop the recording and just measure the number 3 times to get an average of the magnetic field at that position. And then we start the voltages.
Yep.
So you can start the voltages.
Alright, we have about 2 volts going through it, and I'm turning the voltage on.
And there is a change. You see in the magnetic field, there's a slight change in all of them. So there is a magnetic field being produced by the copper loop. And then we stop the voltage, and then we increase the voltage each time. And for this experiment, we did 3, 6, 9, 12, and then 15 volts.
What is this? And then compare to F times delta T.
And then we do the same thing, but for the solenoid, where we hook up the Pascal to the copper wire. And after that, we turn the Pascal on and get the data readings from the magnetic field sensor.
And we made sure the magnetic field sensor is in the middle of the solenoid, in the center.
And same thing for the straight wire. We'll just measure the magnetic field of the Earth and subtract it from our battery.
And we want to make sure right here, the magnetic sensor we found was right here, so that's around 1.5 centimeters away from the long straight wire.
Well, our main goal was to plot B versus I. B is the magnetic field, and I is the current. And then we extract the permeability of free space from the slope. This was our formula. The Biot-Savat's law. Hopefully I said that right. I'm not sure. We first use a long straight wire, a circular loop, and a solenoid. These are our formulas. Extracting the permeability of free space from the slope. And equipment. And these are our data sources. So I'll go back for the long wire, we got y equals 14.64 for a slope. For the loop is 11, and for solenoid 41.896. And this calculated to 1.3799 e to the negative 6 for the straight wire, and 1.2844 e to the negative 6 for the circular loop, and the solenoid is 1.2150 e to the negative 6. The accepted value is 1.2566, so we were very close. At least the first one was a little off. We got a 9.8% error, but the last two were very well done, and we got 2 and 3% error. Some sources of uncertainty, and now some extra information about magnetic fields. It's not just used to get to find the permeability of free space, but you can use it. Well, it's used all over, except one exception or one example is the ribbon microphone, which is a microphone that has 2 magnets inside of it with a thin aluminum strip suspended between those. And when you speak and sound waves physically hit the strip, it moves. And as it moves, it goes slightly towards a magnet, and the electrons inside the metal shift towards one side, the aluminum strip that is, and it generates an electric pulse. And then this electric pulse can be measured and redirected into basically converting sound directly into signal. And that's it. Thank you very much.